from India. We also talk about his work on cold fusion and
ARC, which stands for Baba Atomic Research Center.
And then the following Friday will be the 29th, and then our SBS students have arranged for a seminar.
From Dr. Coulomb with UC Riverside to speak on Rabi curve space and black holes.
And then the following, the last Friday, we'll have another talk on cold fusion by Dr. Joyce and Eagleton. There's John, who'll talk about what's happening next week, just a few words now.
And next week, the Business High School University Network is meeting in building in room 253, 7 o'clock to 9 o'clock. We have a speaker on from JPL coming to talk about climate history as far as implications for Earth. And there'll be demonstrations and things as usual, and you're all welcome to attend.
So let me introduce Dr. Bob Bush. You all know him. He's going to introduce our speaker. We're happy to have here today with us.
Well, first I'm going to just have a couple of guests in the audience take knowledge, if you wouldn't mind. We're privileged today to have Dr. Ray Fleck, who's the research director at Caltech here, if you would just. And then we have a research director from Southern California Edison, Dr. Kurt Curtis here. It helped us very much with our whole fusion out at Caltech. We're very proud of that. And let's see who else here. Dr. Miles' colleague, Dr. Bush, if you would stand up. He is not related to me, but of course, the Bushes are all brilliant people. We say at the Lake Board Conference this summer, I got up and said that considering what I considered the inevitable historical importance of cold fusion would be, and considering the fact that, of course, Ben Bush is working in the field, I'm working in the field, my son helped Bob and I set up a computerized data acquisition system downstairs. I said that President Bush might only be the fourth most important Bush in the world. Can I tell you the funny thing that happened to my passport when I got to the airport? Well, today we're indeed privileged to have Dr. Melvin Miles from the Naval Weapons System at China Lake, working with the Navy. The paper that he and Ben Bush have become famous for is apparently not his slide, so he asked that I put this on the board. You can see Bush and Legowski from the University of Texas. The University of Texas now one of the preeminent universities in the world. And then Miles and Ostrom out of the China Lake research station run by the Navy there. And this is the title of the heat production during the electrolysis of D2O and cold fusion experiments. It's in the Journal of Electroanalytical Chemistry, 1991. He did not bring any extra copies of this here. However, he's told me that those who would like a copy, if they'll let me know, that I can then tell him and he will send copies autographed for those who might like them. You might want to get his autograph now because later on I understand the price is going up.
Yeah, yeah.
So let me know after the talk that sometimes if you want an autographed copy of this. Cold fusion is obviously highly controversial. I'm sure one of the reasons that many of you are here is it is controversial. Many people have felt that it is perhaps practically going underground or fading away. Those of us in the field know that what has happened is that people are simply now doing very good work but very quiet. Yeah, this is kind of a sample of this. One of the prime criticisms of cold fusion work has been, if this is cold fusion, if this represents a nuclear process, where are the nuclear ashes? Where are the nuclear products? This, I think, is one of the big answers to those critics of where the nuclear products are, or is there a nuclear product? Let me say about Mel Miles that he took his undergraduate work at Brigham Young University, took a degree in physical chemistry with a minor in physics at the University of Utah, so we've got both of those universities involved here. He's been a NATO postdoctoral fellow in Munich, Germany. He has won a Sigma Xi award for best research paper on at least 2 occasions, the local Sigma Xi groups that he has been in. I think rather than going through this whole thing, which is going to cut this talk short, if we do, I'm just going to, without further ado, present Dr. Miles.
I'd like to thank Professor Bush for inviting me here to give this talk today. Report on our work at China Lake. If I get this centered, maybe turn the lights down so you can see a little better. This is a correlated study of measuring excess heat and also looking for helium at the same time in the experiments. This was done at China Lake. Our name changes every once in a while. We're no longer a Naval Weapons Center. We're now the Naval Air Warfare Center. But that's always, Navy's always changing names around. It's hard to keep up. Ben Bush, who was introduced earlier, he was at the University of Texas at that time, and he did the helium analysis because we didn't have a mass spec that could look at masses below mass 10. So helium analysis, we sent the flasks, the gas samples to Texas, and that's where the helium analysis was done. And he would be the one that would know the details better on that part. A little review. You remember in March 1989, the announcement came about cold fusion and started activity all over the world trying to reproduce these experiments. And some people thought they saw evidence for it, and others did not. And skepticism quickly surfaced as well about this effect. And this continued on into April. Criticism, especially by some of the major laboratories like Caltech and MIT, strong criticism there. In Texas, there were reports of excess heat, and also at Stanford, but a lot of people were having trouble reproducing the effect and getting this excess heat effect. Now fusion, hot fusion of deuterium, the deuterons come together. Maybe I can just use this pointer and then go on to fusion products. Either you get either one of these two reactions going to helium-3 or tritium. In hot fusion, these pathways are about equal. But for fusion to take place, you have to overcome a Coulombic energy barrier, which is pretty difficult. And that's one of the major criticisms a lot of people have is how can you do this at room temperature? In the sun, you can do this, of course, because of the high kinetic energies of the plasma and so on, that particles can approach close enough and fusion can take place. It takes place by a quantum mechanical effect called tunneling if the particles get close enough. And you can simplify the math a little bit if you represent the Coulombic barrier by a square potential well. The main thing is the probability of getting through the barrier. The main thing is the thickness of the barrier, the width, the A right here, and the mass of the particle and particles involved, M. And you can see that if your atomic dimensions like in ordinary chemistry, 10 to the minus 10 meters, the probability of tunneling through that barrier is 10 to the minus 75,000, which is 0, effectively. But if you can get closer, much closer within a Fermi, then you do start getting a reasonable probability of tunneling to take place. And in fact, tunneling is how fusion takes place. You do not cross the barrier, you tunnel through the barrier because using the Boltzmann function, the probability of going over the barrier, the room temperature is 0, of course, but even at a very high temperature, 100 million degrees, your probability of going over the barrier is still much smaller than tunneling through the barrier. So everybody pretty well agrees this has to be a quantum mechanical effect to overcome that barrier. Well, how can this take place at ordinary temperatures where you don't get close enough normally? But one thing in electrochemistry, you can create conditions that are quite extreme. For example, for the electrolysis of D2O, you go through the free energy relationships and come up with the equation, which is actually a Nernst equation. You can show that for a potential of about overvoltage, or potential of about negative 0.80 volts, if you put that potential in here in this equation, actually the difference with these two potentials, you can equate that to a pressure of 10 to the 26 atmospheres of deuterium gas. Now, it doesn't mean you really have that pressure, but as far as the electrode is concerned, when you have that voltage applied to it, it is behaving the same as if you had that pressure. You have that same driving, thermodynamic driving force driving deuterium into the palladium, the same as if you applied, if you did it strictly by pressure alone, you have to have that type of pressure to equal what we do simply by potential in electrochemistry. So you can create tremendous effects at the electrode surface through electrochemistry. And with that kind of driving force, you quickly form an alpha phase, which is about, just takes a small amount of hydrogen, 0.003 hydrogen per palladium to get the alpha phase. And then you go on to the beta phase, and you get quite striking changes as you form the beta phase. The lattice increases by 3%, becomes more like an alloy, it becomes an alloy actually, and it has semiconducting properties rather than metallic properties. So you greatly change the material in the process. Well, early on in the story about cold fusion, this appeared in the Los Angeles Times, probably April, I forget, but they were already advancing the theory at that time that the lattice and under these pressures may change the reaction pathway considerably. Instead of the normal hot fusion pathway, where it goes through a helium-4 intermediate, but has such tremendous energy that helium-4 is not stable, and so it splits either into helium-3 or tritium. But inside the metal lattice, if that's where it's taking place, perhaps this excess energy of this excited helium-4, it can transfer its energy to the metal lattice and stabilize itself and appear as helium-4 as a product. With this condition of the metal lattice in the electrode.
It's a little back here.
Right here is what you use? Tell me when.
Better.
Okay, good. Okay, early on in the cold fusion controversy, we started experiments at China Lake. And like a lot of people, we did not get positive results. In fact, we worked from late March until September before we had positive excess heat. We focused mainly on excess heat early on, and like many other people, we did not see excess heat. I think there are reasons for that. I understand better now. These are some of the early calorimetric designs we had. We had just a thin palladium wire and with a kind of a loosely round coil here. One problem that one mistake we made, and I think other people made, is that you need to have quite a uniform electric field for the counter electrode surrounding the palladium electrode in order to get this effect. We had the electrode too long and the counter electrode too loosely coiled. Plus, I think even early on we had the palladium going clear out top of the cell. So even though you drive deuterium into the palladium right here, it can diffuse and get above the solution. There's no electric field up here, and it's free to come back out again. So it's hard to get a high loading under a situation like that. And other people made this mistake also. If you don't keep the electrode fully submerged, you can have problems in trying to get effective loading. Now, the way we do our calorimetry basically is using Newton's law of cooling. We have the heat out is equal to the calibration constant K and the temperature difference inside the cell compared to outside the cell. That's your heat conduction out of the cell. And then we have joule heat in is basically your voltage times your current. Since we're evolving gases, you subtract the 1.53 volts. That's the thermal neutral potential. That is the energy that expend in dissociating the deuterium into deuterium gas and hydrogen gas. If you recombine in the cell, then of course you don't subtract that term. But if the gases are going out and you could burn them outside the cell and get the energy back, that's the amount of energy you would get. We always refer to our calorimetry as a ratio of heat out to joule heat in by this equation right here. And so with X equal to exactly 1, we'd have an exact balance of heat out and heat in. If we're above 1, then we have excess heat. In our early experiments, we did not see excess heat, as I explained earlier. This is a palladium cathode and a platinum cathode, where you would not expect any effect, and we don't see much difference between using the palladium cathode, which is the dark circles, and the platinum cathode over here. We let it charge slowly over a long holiday weekend here. It wasn't turned off, and then we came in and took measurements later, a few days later. But you can see basically in the early experiments, the ratio of heat out to heat in was exactly 1 within a 4% experimental error. And with platinum also close to 1 within experimental error. And so this continued for about 4 or 5 months. We were getting somewhat discouraged not seeing excess heat. More times than not, we still, even today, we don't see excess heat. We still have that problem of getting, we cannot always get excess heat. I thought I just showed this. This is a very recent experiment. This is last week, actually. This is May 4th last week. We're doing a little bit different experiment here. We're doing a co-deposition experiment where rather than starting with a palladium rod, we start with a copper rod, and we have palladium ions in solution. And we electrolyze and we deposit fresh palladium onto the copper rod. And then we do this in D2O, and the palladium deposit is loaded at the same time with deuterium. This has advantage if there's any effect, you can see it much quicker. It's called the co-deposition method developed by Stan Spock at a Navy lab down in San Diego. So we've been working with this effect. It has a problem, however, in that the palladium deposit is an active catalyst, and it tends to float and get loose and float up and stick to the walls above the solution. So we have problems with the recombination going on in the cell. This is a current efficiency. This would be that's 100% current efficiency if all the gases were escaping. That's what we normally see with a palladium rod. It's 100% efficiency. With this method, we don't get 100% efficiency, and this shows how the current efficiency varied with time. This is the heat that we measured, and it looks like we have an excess heat. You don't see the X value over there, but this is the break-even line right here. So you would say, well, it looks like there's excess heat, and there is. But the excess heat comes from the recombination of D2 and O2 gas going on within the cell. If we take the current efficiency and make a correction for that, then this is our excess heat. And with experimental error for this experiment, you see that we're, on the average, it averages out for thermistor 1. We have 2 thermistors in each cell. Thermistor 1, we average 0.995. With an experimental error, no excess heat. For thermistor 2, averages 1.006. About a 2% error in the measurement. And if you average both of these out, you get 1.0005, the ratio of heat out to heat in. But I just want to point out that even when we do have a disturbing effect like recombination, we can measure the heat, but we can correct it and still show that there is good heat balance within the cell by our calorimetry. Well, it was not until September 1989 that we ever saw any excess heat effect. And we did not see it until we went to this different design. We obtained palladium rod from Johnson Matthey of a thicker diameter, 0.635 centimeter diameter. That's about the thickness of an ordinary pencil, about a 1/4 inch thickness. And we surrounded it with a much tighter coil. At least, the coils are not so widely spaced. They're more compressed about the cathode. And the palladium is completely submerged. This is a nickel lead wire coming out. Palladium is completely submerged at all times and ran it in this type of configuration. And with that type of experiment, for the first time in September 1989, we did find excess heat in one cell, not necessarily in the other. The dark circles are cell A. The open circles is a different cell, cell B. But you can see after about 6 days, we started getting excess heat, up as high as 30%. 30% more heat out than coming in. The other cell was arranged a little bit differently. The coils were not so tightly compressed. They're more widely spaced again. And in that cell, there was not any clear evidence, maybe a little bit here, but not nearly as clear evidence as the other cell for excess heat. Now, we've calibrated our cells many different ways, many different times over going on almost now a 2.5-year period to get this, what we call the calibration constant. We see no evidence that this really changes significantly with time. This shows a calibration that actually extended over about a 6-month period. Some points are in H2O, those are the circles. Other calibrations are in D2O. You can see they all basically fit on the straight line. This is the power that we put in. In this case, we used a resistor, a 20 ohm resistor. We didn't have any electrochemistry going on. We compensated that. We had to do some mechanical stirring to keep things mixed. But you see we get a nice linear fit of power out versus the change in temperature, the difference in temperature inside the cell and that of the water bath, that's delta T. The correlation coefficient is 0.9997, which is pretty good correlation coefficient. Note, however, that it does not go exactly through zero. The line does not go exactly through the 0 point here, and there is a reason for that, and that is some heat does escape through the top of the cell. It does not go through the water bath. And you can model that and explain why the intercept is not zero. Most of the heat does flow from the cell to the water bath, but there is always some heat that goes from the cell to the room temperature air. And you can break this up into two effective constants. On top, that's why we have a T there, and go through some algebraic calculations, which I don't take time to do, shows all the details here. But you can take this equation and rearrange it, take the derivative with respect to temperature, and show that you would expect a straight line. Except the constant that you get is the sum of the two constants for the flow through the bath and the flow through the top. But as long as you keep the bath temperature constant and the room temperature constant, it'll work out okay. It should always be a linear relationship. And you can actually go through some more mathematics and show that even when the power is zero, you won't get exactly delta T necessarily won't be zero when power is zero. And you can actually find the relative values for the constant for heat flow through the bath versus the constant for heat flow through the top. And basically, 6/7 of the heat goes in this direction, but we do lose 1/7 of the heat out the top. But this, you can still do good calorimetry despite this effect, as long as you keep the bath temperature and the room temperature fairly constant. But you got to be careful. Room temperature is a source of error when you do this. Fleischmann and Pons also have this problem. They've been working to better insulate their top and things to try to reduce the heat flow out the top. But in many people's experiments, that is another source of error that has to be considered. Well, we published an earlier paper, actually two earlier papers. The first was a negative paper in Journal of Fusion Energy, where we did not see any excess heat. Then following that, we published a positive paper reporting excess heat from calorimetric studies. And then I teamed up with Ben Bush by telephone conversation. I'd never met him before, but I knew how to do the experiment and get excess heat. And he believed he could do the helium measurement at the University of Texas. So we set up a collaboration without ever actually having met before by telephone and decided to do two things now, trying to figure out, is this fusion? Look for the nuclear debris. Almost any fusion pathway should produce either helium-3 or helium-4. And he thought he could detect this at the University of Texas if I could get him gas samples from our experiment and try to see how this correlates with time, the heat and helium, how they correlate in time. When we get excess heat, is there helium being produced? Yes or no? That was basically what we wanted to answer. And we realized we'd have to run control experiments. We found nitrogen flush gas was a good gas to use because we could not detect helium in the nitrogen, boil-off nitrogen. We tried argon first. That was terrible. A lot of helium in the argon. But the nitrogen, boil-off nitrogen, we could not detect helium in that, so we used that for a flush gas. And we purposely added a little bit of air to determine our helium detection limit. And later on, we ran H2O experiments exactly the same way to see what would happen in that case as a control. Now, again, this just points out, just a reminder, why we were looking for helium. The hot fusion pathways, all the hot fusion physicists think we ought to be finding these two products, but other people have proposed other pathways for helium-4 when the metal lattice is present, or helium-3. This is Professor Schwinger proposed this. If there's always a little bit of hydrogen as impurity, you could get helium-3 in heat. That'd be the only products. We were actually hoping this would be the case, because if we saw helium-3, there would not be much question, because there's hardly any helium-3 in air. Helium-4, you're going to always have a controversy, because that does exist in air. And there's even a pathway involving lithium-6, that gives helium-4. This is the design that we set up at China Lake that shows how we collected the gases. This is a schematic of the cell. We had thick rubber vacuum tubing here and connected to a 500 milliliter sample flask. And then we would run this out through an oil bubbler. So this is always under positive pressure. That would reduce any chance of air leaking in. Before we attached the flask, we would flush thoroughly all connections with this boil-off nitrogen. We'd back flush through the cell by putting a needle valve through the septum, using that as a one-way valve. We'd make sure we flushed out these little glass spaces right here, make sure no air sitting in those or over here. We thoroughly flushed out this side as well. And besides that, we would let the flask sit there with gases being evolved for at least 2 days, often much longer. And the rate of electrolysis would be sweeping the gas out about 19 times a day. The amount of gases we were producing by electrolysis would be equivalent to flushing this flask out 19 times per day, in addition to all the other precautions we took in setting it up. Well, we started this experiment in October of 1991, and we set up 2 cells. We didn't know for sure whether we'd get excess heat, but we did turn out that both cells started to produce excess heat. I only show this starting with day 12 because we did start and stop a few times trying to correct for gas leaks. But by day 12, we were getting excess heat in cell B, and later we saw excess heat in cell A as well. The first gas sample we collected was right here when, within experimental air, we were not producing excess heat. I say this is within experimental air. This flask did not show any helium. Then a few days later, on a Sunday, I collected this sample because I came in and had a large excess heat measurement that day. And that was rather surprising because the room temperature was a little bit cool that day because cold weather had set in a little bit up at China Lake, and the laboratory cools off on the weekend when they shut things down. The room temperature was really kind of out of control, but if anything, that would meant that this excess heat was probably even larger because of the cool laboratory temperature. But that was the second sample that we collected, and that later, as we see later, that showed large amounts of helium. And that was our largest excess heat that we ever saw, was this point right here. We always hoped for another even bigger. You always wanted even bigger and be even more reliable, but we never see that again. So we collected a sample here and also another sample here. And this continued on until into Christmas Day was when we finally turned it off. But before I go on with the rest of the data, I'd like to respond to some possible questions revolving the calorimetry. How can you be sure that you're not getting excess heat by recombination? As I pointed out in an experiment we ran last week with the co-deposition method, recombination does give excess heat. And so you need to know for sure that the gases coming off are not recombining. So if you can calculate theoretically how much gas you would expect at this current density, at our pressure in China Lake's about 700 torr, at this temperature, you know, just using idle gas type calculations, and you would predict with Faraday's law, you calculate theoretically 6.73 milliliters per minute of gas that should be evolved. We measured this experimentally by displacement of water and got 6.75 and 6.69, and with experimental error, we got the theoretical amount of the right amount of gas coming off. And everybody that's done cold fusion experiments with a palladium rod that is totally submerged in the D2O never see any recombination. Recombination is not a problem with a palladium rod. It's only a problem when you get a loose catalyst that floats around and gets on the walls. And we've never seen recombination in a palladium rod experiment. Now, some people argue you get excess heat because you're charging the palladium with deuterium. That reaction is exothermic. This is the value. It's hard to say exactly what it is because it does vary with the stoichiometry here, but that's a good average value for that exothermic reaction. Even if you concentrated that loading over an 8-hour period, I think the loading takes place over several days, but suppose you load it over an 8-hour period. What kind of power are we talking about by this effect? If you go through this calculation, we're talking about a power of 0.0253 watts. Our experimental power is around 2 watts, right here. So the percent error of that effect is only 1.3%. So it's a small error, even if you load it totally over an 8-hour period. If you load it more slowly, then it's even smaller. Another question is about D2O evaporation. That carries heat away. How big effect is that? We experimentally measure evaporation as 0.19 cc's a day. You can calculate that in terms of watts, 0.00541 watts. That's even a smaller percent error, plus 0.27%. Furthermore, these two errors have opposite signs, so they also tend to cancel. Besides being small, they tend to cancel. I mentioned that we measured the cell constants many, many times over a 2.5-year period. This shows some of our values in D2O, H2O, and D2O again by joule heating. These are thermistors 1 and 2 in the first cell. These are thermistors 4 and 5 in the second cell. You can see that experimentally they all agree quite well within about a 2% error. And even that is not too surprising because the cells are not set up exactly the same way every experiment. Sometimes we have a little more insulation at the top than others, so you can't say these are exactly the same experiments. Joule heating is certainly different than running electrolysis. Yet, the constant agrees quite well. Water is also quite close to what we get with D2O. Question?
Pretty important that when balancing your heat flow.
Right, yeah.
They change over time.
We haven't seen any effective change over time. Like I say, these constants come from we've been doing this for 2.5 years. The constants we use now are the same as we started with. We're using the same cells and we're still using the same constants.
Could that change, but this would explain the difference between 10%?
If you got a 10% excess heat, it's a linear effect. So if you're getting a 10% excess heat, then you'd have to have a constant change of 10%. And in fact, I'm going to come to this in a minute. Nate Lewis at Caltech explained away his measurements by changing his cell constants. He reports his cell constants change, and he reports changes as large as 14%. Now, if I said there's no excess heat, the only thing that's happening is my cell constant changes, and then instead of saying 30% excess heat, I'd have to say my cell constant changed by 30%. But I've never seen any evidence that the constants change. I've gone back and done joule heating several times. There is no change in the cell constant. So the cell constants, as far as I can tell, have not changed in 2.5 years. Now, how does our results compare with other people? Well, this just compares it with the Fleischmann and Pons result. They report in this publication here, they plot the log of the excess heat in terms of watts per cubic centimeter palladium. This is their excess heat. This is the logarithmic scale versus the log of their current density. So that 2 here, that'd be 100 milliamps per square centimeter. This would be 1 amp per square centimeter on this scale. We normally work around 100 to 200 or 300 milliamps per square centimeter, so our data comes right in here. That's one of our data points for excess heat. That's another. I drew the line through their data. It does seem to be a linear effect through this region. You see that our data is right in line with their data. For the same conditions, we get about the same amount of excess heat. I wanted to say a few words about the Nate Lewis paper at Caltech. They did a tremendous amount of work in a very short time. You got to remember this announcement came out at the end of March, and they had their paper submitted by May 23rd, I believe. They had to become world experts in many areas like calorimetry in a very short time period, and I think they failed in some of these effects, at least in calorimetry. Because you're asking about cell constant changing, we'll go directly to their results. They claim no excess heat, and you can go to the Nature paper and look this up. This is their calibrations in water, and I think that's the best place to calibrate. Then you would assume there's no excess heat. They report it as a heating coefficient, which is simply the reciprocal of what I call a cell constant. My cell constant is watts per degree. Their heating coefficient is degrees per watt. So it's just reciprocal. In water, they get 12.6 and 13.1. They go to the D2O experiments, and early on, this is the first 14 hours where you wouldn't expect excess heat, they say their constant is 14. You see, as time goes on, their constant gets larger and larger. They say there's no excess heat, simply their cell constant is becoming larger. But why? I've seen no evidence why cell constants change like that. I think this is evidence that they had excess heat. And in fact, if you start from here and go down to here, you've got about a 12% excess heat effect. They just rationalize it away by saying the cell constant is changing. Furthermore, they claim they did not see helium in their experiment. But their detection limit was 1 part per million. Theoretically, on our helium that we were getting, theoretically, when we calculate it based on our excess power, it comes to in parts per billion range. They would never see helium at the level that we were looking for it using a part per million detection limit. We could never see it with that type of limit. You have to use more sensitive methods. And in fact, they even refer to that down here. They refer to the claimed levels by somebody else, by Walling, 1 to 10 parts per million, or 30 to 300 times the expected yield. So they even admit that in the paper, that the reported levels of 1 to 10 parts per million are 30 to 300 times what you'd expect. Yet they only use a detection limit of 1 part per million. I have tried to point out errors in the Nate Lewis paper by a letter to Nature, but they refused to publish it. And the only thing I've got back is I've heard from other from Business Week, they claim our results are without scientific merit, whatever that means. But I've got a simple algebraic analysis in this where my 17-year-old daughter can follow the logic, and I don't see any algebraic error. But you can show the way they did their calorimetry that they could not really say whether or not they had excess power. They run it when the resistor power is 0 and when they apply a resistor power. And so you get these two terms. When you go through this, the algebraic expression, they claim since the total here, the electrolysis power and the resistor power, and minus the electrolysis power alone, stayed effectively constant, there's no excess heat. But you can show algebraically that all that shows you is the difference that would only prove the difference is 0. In other words, it did not change very much when they changed the electrolysis power and replaced it with resistor power. It just shows the difference is close to 0. Not that the net excess power is 0, just that the difference is close to 0. And they don't point it out in their paper. Another early paper was from Harwell in England on calorimetry. It's not a very good view graph, but again, quite a few authors on that. And one of the very early, also negative and very influential papers in affecting public opinion was by the Harwell group. But if you look at their calorimetry, you see some unusual effects. After 10,000 minutes, I think that is. Well, that's about 7 days. After running 7 days in D2O or Li or water, either one, they are running about 38% negative of break even. In my worst experiment, I've never seen an effect like that. A high school person should do better than running a 38% deficit of breaking even in calorimetry. If they can't get any closer than that early on, I don't know how you can believe anything else in that paper. How can you be so far off? 38% below the break even. This is their percent XSE. This is where they should be if they're just breaking even. They got an error here of 38% after 7 days. Not only that, when they go to another method, they use a small electrode. I mean, this looks impressive, but they've got a small electrode in a volume of 1,000 milliliters. You can't expect a tiny electrode to make much change in that big a volume. To do good calorimetry, you cannot use such huge volumes of electrolyte unless you want a negative result. That's a sure way to get a negative result if you want. Well, continuing on with our calorimetric studies, we tried different things. We were hoping to activate indium foil by neutrons. That's why we inserted that here. So we were doing different things, but we did collect another gas sample here. The arrows are where we added D2O. This is their current density. So this continued on into November and into December. We didn't see any activation of the indium foil, so there's no sign of neutrons that we could detect at least. That just means probably less than 10 to the fourth neutrons per second being produced, which everybody more or less agrees with these days. Thanksgiving or in December, we collected other samples. We put gold foil in, trying to activate gold foil. It has a longer half-life, and I could ship that off to another laboratory where my brother works as a nuclear engineer, and he had better equipment to test for activation. So we inserted that here and collected other gas samples along the way. And into December, we collected our last gas samples on December 17th here and here. And then towards the end of the experiment, we put in, took out the gold foil and put in dental film that I talked about the experiments with my dentist the week before, and he gave me some dental film to try. So that was why we did this. We put those in the cell right here and continued on and turned it off on Christmas Day. We did not ever see activation of the gold foil, but when we got the dental film back, we did see some evidence. I actually sent it back to the dentist. He developed the film and wrote his comments. He said cell A was totally exposed. And this film was not in the electrolyte, but it was wrapped around the cell, on the outside glass of the cell. It wasn't right in the electrolyte, but so any radiation would have to go through this glass cell wall. Cell B was positioned further away and lower in the cell, and so the lower part was somewhat shielded by a Teflon pedestal that the palladium sat upon. This lower part, any radiation reaching it would have had to gone through the Teflon, and you see we have less exposure here. We have some bright spots here because the film was sitting in the outer jacket that had water in it, and so it did get a little waterlogged. And when you peeled it, some of the emulsion did peel away, and this is just what we see right here. But it's totally exposed except for the peeling away of the emulsion. This is a control experiment that went through the same procedures and a little bit of background cosmic radiation, a little scattered exposure. This was a fresh film with no exposure, and this is a fresh film that he exposed with 70 kilovolts, 7 milliamps for 0.5 seconds. He just decided to do this on his own. I didn't ask him to do this, but he sent this back along with the results, showing what a fresh film totally exposed would look like. Well, in the meantime, I had sent the gas samples off to Texas. We usually waited till we had four flasks. So they had a special box that held 4 flasks, and we shipped 4 off at a time. In Texas, Ben Bush received these flasks, and to do the mass spec analysis, there's a lot of deuterium in here of mass 4. Now, deuterium of mass 4 is going to be a very big interference trying to measure helium for. Therefore, we pass this through a chiral filter. This is activated charcoal at liquid nitrogen temperature. This would remove the deuterium and oxygen gas. One filter was not quite enough, so we even went through a second filter. And so any D2 and O2 gases got hung up in this activated charcoal filter at liquid nitrogen temperature, and mainly only the helium would go on through to the mass spec. An example of what a mass spec result would look like, we always ran this on the highest sensitivity of the mass spec. There was always some contamination of hydrogen, either from moisture in the mass spec or hydrocarbons in the mass spec. You couldn't get away from, on the high sensitivity, seeing a little bit of hydrogen. Had nothing to do with our experiment. It was just always a residue of hydrogen in the mass spec. But we would see the helium peak, and we could baseline separate, if any D2 did get through, which it did occasionally, you could baseline separate the helium-4 from the deuterium gas. And furthermore, you could identify the two if you had any question by lowering the ionization voltage and tell which one was which. There's a slight difference in mass between the helium-4 and deuterium. I think it's 0.025 mass units, atomic mass units, if I remember. There is a slight difference, and that's what shows up there. There is a very slight difference. But if you have huge amounts of deuterium, it'll swamp out, trying to find small traces of helium. So, and that's why needless to know, people could not go below that detection limit of 1 part per billion, or 1 part per million, I mean. We could detect down in the parts per billion range. That's where we had to look. But we could resolve the helium in the presence of D2 as long as there was not too much present. We had some references. You could lower the ionization voltage if you had any question, and it would turn off the helium peak before it turned off the hydrogen peak. So you could distinguish if you had a question. We looked for helium-3 always in each experiment, but we never found it. Doesn't mean it wasn't there. It just means it was, if it were there, it was below our detection limit. It doesn't prove it was not there at all, however. Now, if you do a calculation and assume the reaction that was going on, and we don't know if this is really the reaction, but let's take this as a possibility. Deuterium fusion to form helium-4, and rather than giving out the gamma ray, it gives up its energy to the metal lattice and appears as heat in the cell. Then you go through this calculation of 1 watt is equivalent to producing 2.66 times 10 to the 11th helium atoms per second. Now that sounds like a large number, but if you do a calculation on this, at 1 watt, you'd have to operate for 73,000 years to get 1 mole of helium. So that's not a large number. I mean, it is a large number, but it's not a large amount of helium. You'd have to operate continuously 73,000 years to get 1 mole, 4 grams of helium. You can calculate the number of helium atoms you'd expect in the fluent gas because we know the current, we know how much gas we're producing and how long it takes. It takes us, we get 1 minute to get 6.73 milliliters, and you go through a calculation, you would expect theoretically 5.4 times 10 to the 14th helium atoms in 500 milliliters of the gas. At our wattage, we weren't getting 1 watt, we were getting 0.46 watts. So we correct for our lower power. For our operation at 0.46 watts, we should be getting 5.4 times 10 to the 14th helium atoms in the time it takes to fill that flask up. So that would be what we would expect if this were the reaction, the amount of helium that we would be measuring. From our calibration samples using nitrogen, which are not really the same as using D2 and O2, but assuming it's the same, our detection limit was about 10 to the 12 atoms of helium in 500 milliliters. That's as low as we could detect. But we found that when we had high excess power, we saw a large helium peak, about 2 orders of magnitude larger than the detection limit. So we assigned that a value of about 100 times greater than the detection limit. So these are very rough values. All we can say is within an order of magnitude how much helium is probably there. Roughly 10 to the 14th, which is within our experimental error, within the theoretical amount that we calculated. when we had higher excess power and heat, we saw, in general, more helium. When we had little or no excess power, like down here, we saw no helium. It was below our detection limit. And then we had other values in between. The main limitation on this is a measurement of the helium. We're working on better methods of quantifying the helium, and we have a commercial laboratory that now can do that better than what we did then. If you graph this out, the helium atoms that we get, this is in numbers 10 to 14 versus excess power. You would like a nice linear line, but within our experimental error of order of magnitude, this is the best we get. We see a general trend when we have higher power, we see more helium. When we see little or no power, we see little or no helium, and then we have a point somewhat in the middle. We would like to be able to do this much better, where we could get a good straight line, and that line the slope of that line would be the energy of the reaction. It would help to identify the nuclear reaction if you could measure the helium and excess heat and power that accurate. Well, in order to satisfy anybody about this, we had to run water controls, and so we did this in January. We did the same experiment except water in place of D2O, exactly the same cells. We used the same electrodes that we used before, the same gas lines, everything the same except water instead of D2O. And we collected the samples and sent them off, and in none of these samples was helium detected. So in the controls, we did not see helium. And furthermore, in one D2O experiment with no excess heat, we found no helium. Overall, then, we had 14 experiments. I think 6 in water total. I think we have one missing here, but we had 6 in water and 8 in D2O. Well, no, what it is, we had 6 with no helium in water and 1 with no helium in D2O. That makes a total of 6. No, there's 5 in water and 1 in D2O. That makes a total of 6 with no helium. Then we have 8 in D2O with excess heat and helium. So in total, we had 14 experiments that agreed. When we had heat in 8, we had helium in 8. When we had no heat in the 7, we had no heat in the 7. The probability of that happening by chance is 1/2 to the 14th power. It's like flipping a coin, writing down what do you expect to get when you flip a coin 14 times, writing it down in advance, and then trying to get exactly that sequence. That's your probability of that happening by chance. Our control experiments, the nitrogen, no helium in the nitrogen, no helium in the water. We sent sample flasks with nitrogen back and forth to see if they leaked. We never saw leakage during ground transportation, but we did see one case of leakage in air transport. But we could not ship D2 and O2 by air because it's against the law. It's an explosive mixture. We always shipped the samples by ground. But going up in the airplane, the pressure changes, and I think you have more chance for leakage if you ship by air, which we did not do. Well, the main criticism of our results that has appeared is the helium can diffuse through glass, and that is a problem, possible problem. This is the equation for helium diffusion through glass. Depends on the glass. There's a constant for each type of glass. The pressure difference between helium outside and helium inside and the thickness of the glass. This controls the rate of diffusion through glass. These are some constants. And these calculations indicate, at least for Pyrex that we use, that it could possibly be a problem. So we checked this out. We knew when the samples were collected, when I collected them in China Lake, and we know when the samples were analyzed in Texas. So we know how long these samples sat between collection and analysis. The longer they would sit, if helium were diffusing, you would expect to get more helium as time went on, if it were diffusing from the air into the flask. This is our D2O experiments. This is the time that the flask sat where helium may have diffused in versus how much we found. These are the D2O results, the dark circles. They're scattered all over the place. If you try to draw a correlation, least square correlation, you get a negative correlation, not a positive. There is no between collection and analysis. So there is no experimental effect to support any diffusion through the glass. If you throw everything in, including the water and nitrogen, you get this straight line, which is not much better. The coefficient is very poor. But you can see that if helium diffusion to the glass were a factor, there should have been a definite correlation, and there was not. One argument we have used to explain this, and it still needs further research to be settled, is if you have a flask full of deuterium, you've got a lot of deuterium diffusing out. And deuterium and helium are about the same size, and it's been shown in other studies, iron, for example, here, that D2 and helium diffuse through glass by the same mechanism, the same lattice sites. Therefore, you have a huge amount of one going out, it could hinder the other trying to come in using the same sites. And therefore, the fact that this is full of deuterium could really slow down the flow of helium back into the flask. So that's a possible explanation of why we did not see the diffusion through the glass. And in fact, an early paper back in the 1920s in Nature, 1927, it shows that you can actually flush helium from glass by the hydrogen sparges it out of the glass. In fact, he thought he was making helium early on by electrolysis, but he was really just flushing helium from the glass. So hydrogen will actually even displace the helium from the glass surface. Has anybody else came up with results supporting our helium? We'd like to see somebody duplicate our experiment, so I'm not aware of anybody doing it exactly the same yet. But in Hawaii, Liao and Liebert had an experiment that produced a huge amount of excess heat in a molten salt electrolyte. And when they had their electrode analyzed, they found an enrichment of helium in the electrode, significant at 12 standard deviations. When they ran it with LIH, see LIH or LID is the fuel here, and when they ran it with hydrogen, the helium was depleted out of the palladium in that case. A recent paper that Blockers has submitted, is not yet published, his electrodes were analyzed, and he found that out of 9 out of 10 palladium electrodes, he found helium-4, 2 to 100 times the background. No helium-3 was detected. So this agrees with what we found. We didn't find helium-3, we found helium-4. The largest amount of helium was found near the surface, and this is what we believe too, because if the only way the helium could get out into the gas stream so rapidly would have to be a near-surface reaction, and this is what Baucus is finding too. Most of the helium that he's finding is in the surface regions. This just shows some of our calorimetric results in water. Early on, in this paper, in fact, we reported maybe some excess heat, but we found we had an error in our calorimetry because of dental film being in the cell. We were trying to see if dental film was exposed here as well, and it was not. But basically, when we corrected for the errors, we did not see excess heat in water. We saw no dental film exposure in the water. Now, like I said, less than half of our experiments produce excess heat even today with palladium rods. This shows some in February and March where we essentially break even. So the reproducibility is still a problem in the Fleischmann-Pons type experiment, getting this excess heat effect. They now claim better results by using a palladium-silver alloy. We hope to try that. Maybe that will get better reproducibility, but that is a problem that exists with the Fleischmann-Pons experiment even today. In summary, we found excess heat in the palladium D2 LIOD system. Our highest value is 1.3 watts per cubic centimeter at this current density. We found helium in the fluent gas that corresponded to when we saw excess heat, and it was not there when we did not see excess heat. We did not see helium-3, and we ran control experiments with water that also failed to produce any evidence for helium-4. If I have time just for a few minutes, I want to just report briefly on a new experiment from Japan. Takahashi gave a talk at Texas A&M that I went to a week or two ago. I'll just take a few minutes of his results. This has been in the newspapers, at least some newspapers. He claims excess heat in nuclear products, neutrons, from pulsing. He uses it doesn't run at steady state. He ramps the current up and ramps it back down, keeps it under a non-equilibrium condition. And he claims he gets a large excess heat effect by using a palladium plate. This is his old design. This is the new design that works. he has a palladium plate that's surrounded by a cage, a symmetrical cage of the other electrode, the counter electrode. And so he is driving palladium equally into the front face and the back face of that palladium plate. And using this design with this very symmetrical arrangement, he has claimed large values of excess heat as well as neutrons. This is how he ramps his current. Early on, he ramps it from 1/4 amp up to 5 amps in a 20-minute period, then drops it back to the starting point, ramps it up again, and drops back to the starting point. He does this. This is called his preloading for 7 days, and then he goes to a low-high current where he goes from a low current of 1/4 amp, and then a step up to a 4.2 amps, and this is now a 6-hour cycle, and continues that on and on. And using that method, he has found, well, I think there's still some questions with his calorimetry. His calorimetry is not the best, but with his, if his large effects is true, I think he can get by with the poor calorimetry. So he's measuring excess power here, low current and high current. He's up here almost up to over 40 watts of excess power. Now, if you're getting that kind of excess power, you can get by with poor calorimetry, if that is real. But he gets more excess heat with the high current than he does with the low current. At the same time he's measuring neutrons, these are his excess neutron count. So you see he gets more neutrons also at the higher current than the lower current. But in both cases, he is measuring excess neutrons. Neutrons are his expertise. He's really, as a physicist, more expert at measuring neutrons than doing calorimetry. And this is some of his conclusions on cold fusion that he presented. He believes this theory, cold fusion, is a multi-body fusion of hydrogen isotopes inside the palladium. Maybe 3-body collisions of deuterium, or even 4. He thinks he can get powers over 100 watts per cubic centimeter. Very low neutron. It does see neutron, but it's a low level. And he thinks he could even see this in the hydrogen deuterium system, as well as the pure deuterium system. However, these are some of the problems. He tries to do helium analysis on his experiments later. And he made this statement by Faraday: nothing is too wonderful to be true. That's his wording that he concluded his talk with. So then I'd like to thank you for your time and attention. And
We got time for some questions, so we're gonna. I got a simple.
We thought about scaling it up, scale it up by order of magnitude.
the size,
Would be very good way to do it. You get more to the city.
yeah, we could do that. We don't have a, see, right now we're running at almost the limit of our instrumentation for the current density we're running. If you scale it up, to keep the same current density, you're going to have to scale up your current density. So we would have to get some different instrumentation in order to do that. So that's one of the limiting factors is, like Ben is saying, money to do that, without buying new equipment that can run to higher current densities. We're running at the maximum current density that we can run right now with what the equipment we have. And if it's, one amp is the limitation. Well, the equipment we're using right now has a driving force compliance voltage of 20 volts. So that limits how much current we can drive through and we're running 2 cells at the same time, and there's resistance in the solution. So if we go much above 600 milliamps, we reach that limit of that driving force of that instrument. We can't drive any higher current through than that. Yeah, that can help, but that can also create problems as well. You're going to, if you're like we're doing when the gases are coming out, you're really chewing up your detail at a very fast rate when you do that as well. So mainly it's equipment limitation for us doing it right now. We would have to change our entire calorimetry is a size, a certain size. We only run inside our calorimetric cell. We only have 16 cubic centimeters of electrolyte, because to do good calorimetry, you need to have a rather small volume when you're using these electrodes, so you can really pick up the heat quite readily. So we would have to completely scale up everything, and that would take money. That's the only problem. Well, if you're trying to analyze the gas Then you want it to always be flushing through the flask to make sure there's no contamination. And that's why we did it the way we reported here. We want this constant sweeping of electrolysis gases sweeping out the flask 19 times a day to make sure the system is kept clean and purged of any air getting in it. And so that's why we continually let the gases sweep through and out the oil bubbler. Okay, question? Right.
Any positive effect you've noticed?
Yeah, it's detail addition. In fact, Takahashi talked about this as well. He reports that when he adds a detail, the effect seems to diminish. Bockwus has reported also for his tritium results that when he adds a detail, the tritium production seems to go down. If this is a surface effect, adding this detail can greatly affect the surface. You say, well, you start with 16 milliliters and go down to 10, and then you add another 6 milliliters to it. That's a drastic change in the concentration. And if you're depending on a surface species, that could greatly change the surface. That could be one reason, is that it's a surface reaction, and you do something to the surface when you add the D2O. Another reason is that as you electrolyze away, you concentrate the electrolyte, and so your voltage is constantly going down. Your electrolysis voltage is constantly going down. And so the amount of power you're putting in is going down. And so your excess heat as a percent is really can be larger when you have a lower power. When you add the D2O in, then you go back to the higher voltage, even though the power stays the same, percentage-wise, it can be greatly diminished by the fact that you're now operating under a higher power condition. Even though the percent of excess power is the same, it'll be a smaller percentage of the total when you add the D2O. Yeah, that's a possibility. That's complicated, but some people have done that, where you could just feed it in constantly and have some sort of meter system where you would just add it continually. Right. Right. Yeah. But other people have claimed that when they add detail, sometimes they trigger an effect too. So just like the Takahashi experiment, running at steady state is not necessarily a good thing. Adding detail, that's a drastic change to your system. It's a sudden change in voltage. That can also be a triggering effect and help produce excess heat effect as well. So, and we've seen that sometimes. Adding detail seems to trigger an excess heat effect as well. That's goes back to Takahashi's method, where you don't want to keep everything at steady state. Questions?
Solubility of helium inflation.
Solubility, I know the diffusion is very, very low of helium in palladium compared to, almost very, very small. The solubility,
Palladium rod,
yeah.
maybe had some residual.
Yeah. Well, we actually had, after the experiment, we sent some samples to Rockwell, and they analyzed our original, the palladium the rod that we started with, and within their detection limit, which is pretty good, they're experts on helium detection, they did not see any measurable amounts of helium in our palladium rod. And based on their limit, if we assumed their limit was the amount that was there, they didn't see any, but assuming their limit was the amount, the most helium we could have ever gotten out of that palladium rod would have been 10 to the 12th atoms. That might explain one sample, one low-level helium sample, and that's all it could have explained. The amount of, right, yeah. And this was over many, many days and many, many samples. So the amount of helium in the rod was barely enough to explain one low-level helium result.
You know how to actually get the helium out of the palladium? Vaporize it,
You have to vaporize it to really get it out. You melt it, and that'll dries it out. Boil off nitrogen. We have I guess most major laboratories, I think University of Texas as well, they have a huge tank outside of liquefied nitrogen, and this is the boil off nitrogen that goes through the gas lines in the laboratory. That what boils off that big container of liquid nitrogen. That's what we use. The boil off. That's what we call it. Boil off nitrogen. Not tank nitrogen. Not what you buy in the gas cylinder. No.
Well, I'd like to thank Dr. Miles for a very informative talk. And there has been a videotape made of this, and it would be possible, I think, to purchase these later on if anybody's interested. So let us know if you are interested in copies. I think it'd be about $15 a copy for one of these things. Is that right? That's what I told her.